Hello, I'm Joe Nestor, and this is my presentation on CMOS and optical integration. So this is our agenda for the presentation. It will be a brief introduction, and then we'll speak a little bit about CMOS and optical integration together, and then we'll go through some device examples, and then looking to the future, what the future is, and then we'll reach some conclusions and talk about them. So here's a quick little introduction. Introduction by explaining a little bit about CMOS and why it works so well with optical devices. The basic MOSFET transistors, the PMOS and NMOS, were invented by Mohammed M. Attallah and Daewon Kang at Bell Labs in 1959. These inventions were adapted into the CMOS by Chai-Tang Hsia and Frank Wanless at Fairchild Semiconductor in 1963. Eventually, the CMOS overtook NMOS in the VLSI industry and eventually went on to replace TTL technology. What is a CMOS device? CMOS, also known as complementary metal oxide semiconductor, are transistors that make use of both P and N-type MOSFETs. PMOS transistors are generally used as part of the pull-up network, while NMOS transistors are generally used as part of the pull-down network. A simple schematic is presented below to explain the usage of CMOS transistors in building a simple inverter. So if you take a look at the schematic there at the bottom left, the given figure is a CMOS inverter. Note that the voltage Vn is applied to both the NMOS and PMOS, both gates. So consider when Vn equals 1. This makes the NMOS transistor on, okay? And the PMOS is open circuited. This drives it V out to ground, and so you get an inverted signal. Right, just a quick little review. So why choose CMOS? In the CMOS device, one of the transistors is always off, and hence the device draws power only during switching or toggling between states. Thus, the device is very power efficient. The power dissipated is proportional to the frequency of toggling. Another advantage of a CMOS device is its high noise immunity. Presented below are a few gates implemented using CMOS transistors. Towards the end of the 20th century and the subsequent years, integration of optical systems on a silicon substrate is of growing interest because of their compatibility with CMOS technology. New technologies have been constantly emerging which combine the benefits of CMOS with optical devices. Silicon photonics is one such field that enables electronics and optics to be integrated on the same optoelectronic circuit chip, leading to the production of low-cost devices on silicon wafers by using standard processes from the traditional microelectronics industry. So a question arises as to why optical interconnect solutions are becoming more popular when compared to electrical interconnects, more traditional electrical interconnects. Optical links have several advantages such as lower signal attenuation, high noise immunity, lower dispersion and crosstalk leading to higher bandwidth. Due to the characteristic noise immunity, optical links are not affected by electromagnetic interference, which makes them well suited in mobile systems. However, not all connection links have been replaced by optical nodes owing to the fact that optical links that are certainly more expensive than the traditional electrical links. Hence, there is a need to reduce the cost of manufacturing CMOS-based optical circuits. However, several challenges have been faced and overcome to make such an integration feasible. And if you take a look at the diagram here, in yellow, it shows you the optical components, right? Light source, the modulator, and we have the optical waveguide, photodetector, and then in the gray is the more traditional electrical components, the driver, receiver, front end. So, just to point that out. So, speak of the slow progress of optical integration with CMOS. Several challenges have been faced and overcome to make such integration feasible. It is a well-known fact that optical integrated circuits have progressed much more slowly than electronic ICs. So just to get into the details of why that is. Optical photonic device sizes are determined by the optical wavelength, which is much larger than the electric size limit. Point two, optical electronic devices require a wide variety of supporting devices such as lasers, modulators, etc., as we saw in the previous slide with that diagram. And then point three, optical electronic devices are based on materials other than silicon, which are harder to control in a regular process. So there's a lot more variation. So that's added to the expense and the slower development as compared to the traditional silicon ICs. And so the figure on the left-hand side here illustrates the gap in the development of electronics and photonics owing to the reasons stated above, right? So quite a disparity, as you can see, starting in the mid-2000s to the current day versus 1.9 billion transistors right now. So I think that illustrates well the slower progress. So this is just an example, early example of the integration of optical devices and CMOS devices. So we're just going to talk about monolithic repeaters real quick. Monolithic repeaters comprise transistor detector and amplifier, and laser on a gallium arsenide substrate. This combines 3 to 5 photonic elements with 3 to 5 electronic elements on the same chip. These were not made commercially available. It's an early example, but it's just kind of a proof of concept. Several attempts were made to combine a photodiode with JFET. The focus on this is due to the fact that it can be fabricated in a small area and has low power consumption. But the remarkable capability and success of CMOS electronics has motivated industry research on photonic devices on the same chip as CMOS chips to integrate them. And so several techniques have been invented to integrate waveguides on CMOS devices, which are crucial in optical devices. And so the figure below here, it shows you the waveguide and gives you the diagram of how they physically did it, integrating the waveguide onto the CMOS. So I'd like to first talk about optical devices and CMOS amplifiers. CMOS devices starting from the 90s and moving forward. Amplification of optical signals is definitely an area of importance, especially in fiber optics communications, where we have amplifiers at fixed intervals to counter the attenuation effect of the waveguide. CMOS amplifiers of photocurrents. A family of CMOS amplifiers has been designed to amplify photocurrents. Sensitivity and bandwidth of different components can easily be adjusted by choosing different transistor geometries. These devices assure low noise and high yield in fabrication. The circuits consist of an amplifier circuit and a preamp circuit. The task of the preamplifier circuit is to reduce local parameter variations on the output, and the amplifier circuit, as the name suggests, amplifies the input current signal. And so the image on the left-hand side is the amplifier circuit, and the image on the right-hand is the preamp circuit. So it just shows you the schematics there. So this slide just quickly shows, it's an illustration about photonic integration has developed over the past few years since the early 90s. The passives were the first to be integrated. And then increasing in complexity, you have optical electronics integration, and then we have silicon photonics and optical circuits. So the data presented to this point is from a research point of view. Now we'll move into more practical uses of CMOS and photonics integrated together. So this is just an example, a practical example of HDMI 2.1 standard for HDMI cables. So active optical cables specified by the HDMI 2 standard, 2.1 standard, have been developed for CMOS chipsets integrated on a PCB with connectors at both ends to transport data. Transport the data through plastic optical fibers. So these optical fibers, they're commonly known for their benefits over conventional glass optical fibers, such as lightweight, resistance to stress and strain, and low cost of procurement. And this design is capable of driving a 4K 60 frames per second video with ease. And so these CMOS chips, they use they're 4-channel devices, and And these 4 channels make up the transmitter and the receiver. The data is transmitted through like I said, the plastic optical fiber. And then as you can see down here at the bottom, it gives you a little diagram of what I was just talking about. So this is something I think that a lot of people will be interested in. It's pretty cool. So this is CMOS optical technology for LiDAR applications. So LiDAR stands for light detection and ranging. It's a method used for measuring distances by hitting the target with laser light and measuring the time the light takes to return back to the transmitter. It is also used to detect the terrain of a region and to characterize the terrain in 3D. I don't know if you've ever seen on the History Channel, I think they do, archaeologists will explain that they use LiDAR to image burial grounds or ancient cities or ruins that are otherwise unviewable, that are inaccessible. So a CMOS-based receiver array is used alongside a LiDAR sensor, which can obtain high-resolution images. And then there are also photodiodes working in the avalanche breakdown region that are used to increase the range of the device. And then here on the right, you just have a diagram that illustrates what I was just talking about. You have the light incoming the target, and the light comes back, and it times the light and see what the image for you. And so just to stay with LiDAR for a little bit here, to go into the technical details for a second, as the fiber laser transmits the signal, the timer counter is started. The laser passes through the transmission lens to focus it onto the target. As the signal bounces off the target and returns to the device, it passes through the CMOS array receiver. The timer counter detects the arrival of the signal and stops counting. Using the value stored in the counter, the distance is calculated. The purpose of the receiver array is to improve the object detection rate. So this, like I said, they're using a lot in archaeology. You're able to find things that they otherwise would have never seen. So on the right there, it's an example of Mayan ruins in, I think, Guatemala that they were able to image using LiDAR technology. So pretty cool stuff. So this is a high-speed CMOS optical receiver ICs. An optical receiver is one of the key components in a fiber optical communication system. It converts the optical signal coming from the fiber back into an electrical signal, which can be further processed as required by the device. The receiver mainly contains a photodiode and a series of amplifiers as required. A photodiode is a device which converts light energy into electrical current. For high-speed applications, a PIN photodiode is used. That's illustrated below. So a PIN photodiode consists of 3 regions: a P-type region, an N-type region, which is heavily doped, and it also consists of an intrinsic region. In the intrinsic region, its width is larger than the space charge of a normal PN junction, and the amplifiers used are CMOS amplifiers. So just to talk about augmented reality for a little bit here. Augmented reality, or AR, is an enhanced version of the real world that is achieved through appropriate digital visual elements, sound, or other sensory stimuli delivered through technology, right? This superimposed computer graphic, this superimposed computer graphic images on the user's view of the real world. It is extensively used in 3D modeling. A US-based startup called Magic Leap is working on a light field chip using CMOS-based photonics for this very purpose, for augmented reality. This company was launched in 2010, and it's since made tremendous progress in this field. It's currently worth $4.5 billion. And so the chip that they're working on, the light field, uses this idea that the light is a vector that indicates the amount of light flowing in every direction through every point in space. Taking a light field camera as an example, it records information such as the intensity of light and the direction in which the light rays are traveling, in comparison to conventional cameras, which capture only the intensity of the light. Okay, so let's talk quickly about the CMOS photonics for future transceiver applications. The future transceivers require decreased cost and power, and also increased bandwidth, functionality, and bandwidth density. So I'll speak a little bit about why CMOS photonics possess the perfect solution to these requirements. So point one, high speed of operation. So the CMOS photonic devices are capable of operating at high speeds in excess of 10 gigabits per second. Point two, channel utilization. CMOS photonics, they're advantageous in terms of channel capacity that will allow it to lead industry in terms of channel utilization. And then point three, no modal dispersion. So CMOS photonic devices have higher reach in terms of meters as the single mode fiber, which is used, removes modal dispersion. So to continue talking about the CMOS photonics for the future, the next point we have to consider is power consumption. While talking about power, we must consider two levels: optical transceiver power and overall system power. CMOS devices offer advantages in both these areas. Parasitic and low impedance interfaces are removed, which save a significant amount of power. The next point is device area. So the device area is very small and can be packaged into a small chip. And then to go along with that, the integrated device. Since CMOS photonics is an integrated device structure, there are no more interfaces between the photonic unit and the CMOS unit. This leads to increased reliability. So to wrap up in conclusion, as explained and demonstrated through various slides, which I presented earlier, optical integrated CMOS circuits have numerous advantages when compared to electrical integrated communication channels. Photonic integration is currently an active topic in many defense-related contracts. Optically integrated CMOS devices have high energy efficiency and hence are notable power saving option. These devices find their application in processing industry, safety and security, agro and food industry, and several other billion-dollar industries. And so a huge transformation can be brought if specific interest is focused on these devices. That's my presentation. Thank you for listening.